I apologize to anybody who saw this talk at SVP, but as I had my Viva in between SVP and now, I didn't really have time to make a second talk. So this is some of the work that I did during my PhD. Since I'm the first talk on pterosaurs, just a very brief introduction. Pterosaurs are obviously the first vertebrates to fly and also the largest animals ever to take to the air, which makes them really important in terms of understanding the limit of flight and kind of how far we can go with it. When you think of a classic pterosaur bone, what we generally think of is an extremely thin-walled bone with these kind of cross-sections with this very thin kind of sub-millimeter wall, and that's what is generally thought of as what a pterosaur bone looks like. So this is from the classic Currie and Alexander tubular bone paper, where you get this, for a wing phalanx, you get this kind of sub-triangular shape with, again, kind of less than a millimeter in thickness. And there's several different ways that you can characterize this thickness and compare it between taxa. So the first way that we do this is by looking at radius over thickness, or R over T values. And you can also do it with the K value, which is a ratio of the inner to outer radius in a bone. So looking at this thinness, there's obviously going to be some sort of a trade-off between having the bone be very thin-walled and therefore light, or having it kind of be too thin-walled and then it buckles. So in terms of what this means for stiffness is as the diameter grows and the thickness of the bone decreases, you actually get a stiffer bone. So you get this strength with lightness. But as I mentioned, that then becomes difficult for buckling. So you can't have it be too thin-walled or else the bone will buckle under different forces. So looking at what this thinness means and going back to that sort of classic idea of a thin-walled pterosaur, in the literature you see a lot of references to this being thin-walled, often with no sort of quantitative value to it. So cortex is just thin, and therefore it's a pterosaur. Other papers talk about it being thin as in something like 0.2 millimeters, and then you get thin being something like 2 millimeters. So there's quite a lot of variation in what exactly thin means. And this is so poorly understood that you get specimens that, for example, the one on the top right was said this couldn't possibly be a pterosaur bone because it was too thick-walled. But if you look, it's actually one of the thinnest of all of the examples on that slide, and those are all known pterosaur bones. So we don't really understand kind of the variation of thinness in the bones. A couple of people have looked at this in the past. So the first, going back to that initial kind of classic Currie and Alexander paper, they looked at all kind of aspects of tubular bones. So birds, both flightless and flying birds, pneumatized and non-pneumatized, as well as land mammals and alligators and geckos. But they have a couple of pteranodon specimens up here, which tend to be much thinner than everything else. And this was thought as kind of that classic idea. This is what a pterosaur bone looks like. Hazelhurst and Rayner took it a little bit further and looked at smaller pterosaurs and rhamphorhynchoids and compared it to larger ones and found a little bit of a different kind of distribution. And then Fastnacht did it a little bit more, but looking at just Zungarypteroids versus everything else, and found that Zungarypteroids had extremely thick-walled bones compared to everything else. But what these studies lack is one, numbers. So they're not, I mean, the highest has 42 specimens, which for pterosaurs is a lot, but also they're not phylogenetically grounded and haven't really looked at the variation between different groups. So the first thing that I wanted to do was look at this variation in a little bit more detail and then understand sort of what factors might be driving this variation in cortical thickness. So the first kind of main hypothesis is that this classic idea of all pterosaurs having these extremely thin-walled bones isn't necessarily true. Second is that wing bone thickness is not phylogenetically correlated, contrary to other studies, and also that we will see this difference between what you see between large and small pterosaurs, and that this will be related to pneumaticity. So in order to do this, I looked at a large sample. For anybody who knows anything about pterosaurs, 120 is a lot of pterosaur bones. Tried to look at as many different groups as possible, so I have non-pterodactyloids and pterodactyloids. Most of the specimens were 3D preserved, or at least preserved well enough that I was confident that the radius was the actual radius in question of the bone. So this is all done kind of diaphysis, looking at the midshaft of the bone, and from several different groups. So things like Rhamphorhynchus, there's a lot of Rhamphorhynchus in here, but Rhamphorhynchus and then other large-bodied pterosaurs. So mainly to do this, I was looking at the radius and thickness, R over T values and K values. Trying to understand if there's any phylogenetic signal. I used a phylogenetic generalized least squares model in R, and also looking at lambda, which is a measurement between 0 and 1, where 0 has no phylogenetic signal and 1 has a very strong phylogenetic signal. In order to look at the biomechanics part of it, I was looking at second moment of area, which is a measurement of the kind of distribution of material around the outside of the bone, and this is used as a proxy for bending stiffness. For a circular bone, it's really easy to calculate. You can just do it with this, so it's dependent on the radius. Because most pterosaur bones are not circular, this was done in ImageJ using cross sections, so I don't have as many, I don't have 120 of those, unfortunately. But you see kind of the general values that we're looking at. For a bone like this, you'll get an R over T of about 2.5, and then you get this more sort of classic pterosaur idea with an R over T of 23. So looking at some of the results, main thing that I will point out is there's a lot of noise. So there's quite a lot of variation. You get from as low as about 0.2 all the way up to 5.5, which I'll talk a little bit about later. That's Hetzegopteryx. But most of the specimens tend to fall out between about 0.5 and 1.5 millimeters. Not a lot of difference between the different bones. Some bones have better correlation than others. And not a whole lot of difference between different taxa as well, although this graph doesn't have taxa on it. But the main thing is that it's quite variable, and not a lot of patterns are seen. Looking at that distribution of R over T and kind of comparing it back to the initial graphs, in this sample, and from what I looked at, most of them actually end up on this end of the graph. So contrary to that classic idea of a very thin-walled pterosaur bone, about 65% of the specimens were having an R over T of less than 7. So quite a lot of specimens are coming out as more thick-walled, and that includes things like some Ashdarchoids, ornithochiroids, and things we typically think of as being extremely thin-walled. But in general, the ones over here tend to be those large-bodied ornithochiroids and pteranodontids. Looking at that phylogenetic signal, I used the Antres phylogeny because it's kind of the most recent widespread phylogeny, but I've also tested it with other ones. I just haven't included them here and found similar results. So the first thing is you can see there are actually two lines on here, and they are exactly the same. So the phylogenetic model and the non-phylogenetic model are the same, which shows there's no phylogenetic signal at all when you look at thickness as a response to radius, so kind of thickness in response to size. When you look at these traits individually, we see a really strong correlation for radius. So that has a very strong phylogenetic signal, which makes sense because we know that pterosaur body size is phylogenetically, or there's a phylogenetic signal to pterosaur body size. But thickness, again, has absolutely no correlation at all. So thickness is not, does not have a strong phylogenetic signal. R over T as a single character does come out with a strong signal, but this is probably driven by the fact that radius is so strongly correlated and the thickness is generally quite small. So looking at the biomechanics and second moment of area, we can see there's a general increase as the animal gets bigger. The second moment of area tends to increase, so you get a stiffer bone as the animal gets bigger, which not unsurprising given that we know as it depends on radius, so as the radius increases, this is going to get bigger. There's some maybe slightly different relationships between different bones, but unfortunately, because I had to rely on specimens that A, have a cross-section I can look at, and that's 3D, and B, I can confidently estimate the wingspan. I don't have a lot of sample size for these specimens, but in general, we do see this increase. And then again, you get Hetzegopteryx up here, which is always an outlier and annoying, which I'll talk about a bit later. So looking at the second moment of area compared to K and R over T, again, as the animal or as the R over T and K values increase, you get a generally stiffer bone, except for Hexagopteryx, which is not really following the trend. So looking at what this might kind of imply and what this might mean is, for pneumaticity, we know from specimens and from the literature that Ashtarchoids and ornithocheiroids have pneumatized wing bones. So we can see these nice pneumatic foramina, and we know that this is extremely common in these animals. And they tend to be things that are having an R over T of something over than about 5 tend to be pneumatized, whereas Tsungarypteroids, Ctenochasmatoids, and non-pterodactyloids, currently there's no evidence that they had pneumatized wing bones. And these specimens tend to come out in the smaller ones. So we might be able to use R over T value as a kind of proxy for whether or not an animal is, or a bone is pneumatized. So there does seem to be a link between pneumaticity and the relative thickness. So what this might mean in terms of pterosaur, kind of general pterosaur paleobiology, is the smaller pterosaurs have these lower R over T values, which makes them resistant to both bending and also things like compression and buckling. And compression and buckling are extremely important in terrestrial locomotion and takeoff and landing. So these are kind of more generalized, lots of takeoff and landing and spending time in the air as well, whereas large pterosaurs have completely sacrificed all compression or buckling and are going purely for bending and mass reduction. So we know that large pterosaurs spend, or probably spent most of their time on the air and are not really proficient on the ground, and this is something that's kind of supported by what I've found here. But then we get Hexagopteryx, which throws a wrench in everything that I just said. So Hexagopteryx is the largest pterosaur in the study. It's got a wingspan of something around 10 or 11 meters. The humerus is absolutely huge and has the biggest thickness, so it's got a thickness of about 5.5 millimeters, which is much thicker than anything else we've looked at. And it just doesn't follow these trends. So here, you would expect Hexagopteryx to be somewhere over here, but it's not, it's here. So it has this extremely thick-walled bone. And this is something that might support the idea that Hexagopteryx has been spending more time on the ground. So it's from the late Cretaceous of Romania and has been previously hypothesized to be kind of an apex predator, or spending most of the time on the ground, like Mark's lovely drawing, eating little dinosaurs. So this might kind of support that and show that this animal was much more robust and spending a bit more time on the ground than other pterosaurs of similar kind of age. The problem is that in terms of large-bodied pterosaurs like Hexagopteryx, I have data for only Hexagopteryx. So there's no currently known thickness data out there for things like Quetzalcoatlus. So I'm not sure if this is something that's typical of all large-bodied Ashtarchids or if this is just a question of Hexagopteryx. So moving into kind of those conclusions and back to the original hypotheses, pterosaur bones are not all thin. That sort of idea that we think of is only held true for large-bodied pterosaurs. So a lot of them have low R over T, and this is driven by size. And then wing bone thickness is not phylogenetically correlated, but the relative thickness is, again, driven by size. And we do see a difference between thinness in large versus small pterosaurs, and this is likely related to pneumaticity and size again. And lots of people to thank, especially to SVPCA and the Jones Fenley Memorial Fund. So thanks everybody for donating last night, because they helped get me here. And also, yeah, there we go. Thank you.